Okay, you have to admit this sounds completely insane, right? Not that long ago, training a giant AI model with 16-bit precision was considered the gold standard. Then 8-bit came along, and we thought that was pushing it, but now, just 4 bits? That seems impossible. It's like trying to paint the Mona Lisa, but you only have 16 crayons to work with. The signals that teach the model, the gradients, can only have 16 possible values. I mean, mathematically, a model shouldn't even learn properly. And yet, new research says it's not only possible, it can actually match the performance of 16-bit training. So how in the world does this actually work? First, let's just ground this whole conversation and why it matters so much. Let's talk money. A Stanford report crunched the numbers, and they figured that training a model like Gemini Ultra costs somewhere in the ballpark of $200 million just for the compute. That number is staggering, and it basically puts a giant keep out sign on the door for almost everyone. And this is exactly where our crazy question comes back into play. Because if you could somehow pull this off, if you could drastically shrink the precision you need, well, you'd slash your memory needs, you'd crank up the training speed, and you'd start to bring those astronomical costs back down to earth. But it just feels like it breaks the rules of math. So let's get into how it's done. You know, what's really interesting is this isn't some random leap out of nowhere. It's actually part of a long, steady march. We started way back in the 90s with 32-bit floating point, or FP32. That was the standard for ages. Then around 2018, Google Brain really made 16-bit training a thing. Just this year, DeepSeek showed the world that 8-bit could work for a top-tier production model. And that relentless push brings us right here, to today, staring at the new frontier, 4-bit. Okay, but here's the first bit of fine print, and it's super important. Even though you see these bold headlines like floating point 4 all the way, the reality is a little more complicated. It's really a mixed precision approach. Think of it like a surgical operation. You wouldn't use a sledgehammer for everything. Certain delicate parts, like calculating attention scores, they still need that higher precision. The 4-bit magic is saved for the big, heavy, repetitive lifting. So the solution isn't one single aha moment. It's really a team effort, a perfect storm of innovation coming from 3 different directions. You need the right hardware, you need brand new data formats built just for this, and you need some really clever software tricks to make sure the math doesn't fall apart. So let's break down each one of those pillars. All right, let's start with pillar number 1, the hardware. Because it turns out this whole revolution is basically built on top of a very specific piece of silicon that has become the absolute engine of modern AI. And I'm talking, of course, about NVIDIA's Tensor Core. So what is a Tensor Core? The easiest way to think about it is like a specialized little factory inside your GPU. It has one job, and one job only, to perform matrix multiply accumulate operations. That's the single most common and expensive task in all of deep learning, and the Tensor Core is designed to do it faster than anything else. And here's their superpower, the thing that makes all this possible: mixed precision. A Tensor Core can take in 2 matrices that are in a super low precision, like our 4-bit numbers, multiply them together, and then, and this is the critical part, add up the results in a much higher precision format, like 32-bit. Why? Well, if you try to add thousands and thousands of tiny 4-bit numbers together, you'll get rounding errors and overflows all over the place. Accumulating in a big 32-bit bucket prevents all that mess. So where does this hardware get used? Well, during training, almost all of the heavy computation comes down to just 3 core matrix multiplications. First, there's the forward pass, which is just calculating the model's answer. Then you go backward. You calculate the gradient, or the blame for the weights. And then you do it again, calculating the blame for the activations of the layer before it. And here is the punchline. These are the 3 operations that get the 4-bit treatment. You're not doing everything in 4-bit. You're just taking these 3 huge, computationally intensive steps, quantizing their inputs down to 4-bit, and letting the tensor cores rip. That's where you get the massive speed up and memory savings. Okay, so we've got the hardware all revved up and ready to crunch 4-bit numbers. But what kind of 4-bit number are we talking about? This brings us to pillar number 2, the data format. Because as it turns out, not all 4-bit numbers are created equal. Now, if you've been following this space, you might have heard of something called quantization-aware training, or QAT. It's really important to understand that this new method, fully quantized training, or FQT, is totally different. QAT just pretends to use low precision, it simulates it, but all the math is still done in high precision, so you don't actually get any speed up. FQT is the real deal. It actually performs the math natively in low precision. That's the secret to unlocking the performance gain. To make this happen, a bunch of the big hardware companies got together and agreed on a new standard. It's called the microscaling, or MX format. And the key idea is pretty clever. It's block-based scaling. Instead of needing a scale factor for every single member, you just have one shared 8-bit scale factor for a whole chunk of 32 4-bit numbers. It's just a way more efficient way to pack all that information together. So why go through all this trouble for a 4-bit floating point number? Why not just use a simple 4-bit integer? Well, it all comes down to how the data is shaped. Integers are rigid. They divide up the number line into perfectly even steps. But model weights aren't evenly distributed at all. They're almost always clustered in a big bell curve right around 0. A floating point format is flexible. It can put more of its precious 16 values where they're needed most, right around 0. It's just a smarter way to spend your bits. All right, we've got the hardware, we've got the right data format, but there is one final, absolutely critical piece to this whole puzzle. It's a clever little software trick called stochastic rounding, and without it, all this low-precision math would just drift off into nonsense. So here's the problem with normal rounding. Let's say you're always rounding to the nearest value. What happens if your gradients, the learning signals, consistently land just a tiny bit below the halfway point between two numbers? They will always get rounded down, every single time. Over millions and millions of training steps, this tiny, constant downward nudge can push the entire model way off course. The solution is just beautiful. It's called stochastic rounding. Instead of having a strict rule, you just introduce a little bit of randomness. You basically flip a weighted coin. So sometimes you'll round down, even if the number is a little closer to the higher value, and sometimes you'll round up. Over time, all those little random errors cancel each other out, and on average, the model walks in a perfect straight line, staying right on track. And that's it. That's the whole magic trick. You combine those three pillars, the Tensor Core hardware, the MX data format, and the stochastic rounding trick, and suddenly, 4-bit training isn't impossible anymore. So let's get to the big question. Does it actually work? Is this the future, or just a cool academic fad? Well, the results they published in the paper are pretty jaw-dropping. When you put a model trained in 4-bit right next to a standard 16-bit model, the training loss, how well it's learning, is practically identical. And on top of that, when you test them on standard benchmarks, the scores are incredibly close. The performance hit you take for all those savings is tiny. But, and this is a really big but, there is an important caveat here. The tests they used in the paper were mostly classification style, think multiple choice questions. They didn't really test the models on complex, open-ended stuff like writing a poem or summarizing a long article. And that's a much harder task. So while the results are super promising, the jury is still out on how this holds up for those really creative tasks. So what's the big takeaway here? I think it's that we now know training in 4-bit is technically possible, and it works surprisingly well. It hasn't had its big DeepSeek moment yet, where one company releases a flagship model trained this way and changes the game. But the tech is solid. And as NVIDIA's new Blackwell GPUs, which have native FP4 support, start to roll out, it feels almost inevitable that this will just become the new standard. And this leaves us with one last, really fun idea to think about. We've watched this incredible progression, right? From 32 down to 16, down to 8, and now we're knocking on the door of 4 bits. So if 4-bit training is about to become our present, what about the ultimate frontier? Could training models with just a single bit, a 1 or a 0, actually be our future?